you're asked to find the equilibrium constant for the reaction in which iron 2 reacts with solid silver to give iron and silver ions. So you need to find K for this equation. Now, I guess one way to find K would be to go to the back of your book and find the free energy change of the reaction via the change in the free energies of formation of the products minus the change in the free energies of formation of the reactions. You could do that. But we can also solve for this problem by solving for the standard cell or EMF of this cell. And so we can find K using this equation. Manipulate this equation. So multiply both sides by n, divide both sides by 0.0257, and you get this. And then take, I guess, the anti-natural log of both sides, so you get K is equal to e to the E standard times n over 0.0257. But now you're stuck. You need the EMF of the cell, and you need n, which is the number of moles of electrons transferred in the balanced chemical equation. And so let's solve for both of these. Take this equation and solve for n. Now, you see that you're turning Fe2 plus into Fe with no charge. And only one iron is being reduced, and so it only needs to accept 2 electrons for that to happen. And so you see that iron is accepting 2 electrons, but similarly, 2 silvers are turning into 2 silver ions, and in order for that to happen, they are releasing 2 electrons. Overall, even though it's not written in this equation, you can determine that there are 2 electrons being transferred in this balanced chemical equation. And so your n value is 2. And now you need to solve for the EMF of the cell. So the E cell standard is equal to the standard reduction potential at the cathode minus the standard reduction potential at the anode. Now, what is going to be at that cathode? What will be at the anode? Well, we can see that iron, turning from Fe2 plus into Fe, 2 plus into Fe, it's being reduced. And so iron is being reduced. It must be reduced at the cathode. And so we'll use the standard reduction potential of iron 2 as our value at the cathode. And then we see silver is being oxidized. We'll use its standard reduction potential at the anode. And so go ahead and find the standard reduction potential chart, plug in these values in here, and you should then find that the standard reduction, actually the EMF of the cell is negative 1.24 volts. So now you're able to plug in for E standard, it's negative 1.24 volts. Plug in for N, it's 2, and plug in 0.0257. And so we get, when this times that is divided by that, we get negative 96.5. Take E to the negative 96.5, and we get K is equal to 1.23 times 10 to the negative 42. Oh, does that make sense? Is this reaction spontaneous? Well, we have a negative E cell, so that should be a non-spontaneous reaction. There should not be very much product, and our equilibrium constant is showing that. We have a value much less than 1. You should also know that this is a non-spontaneous reaction because you should know that, that silver and copper and gold are quite unreactive. They're stable. Why should iron be able to displace silver? The silver is something that we use in coins because it is fairly unreactive and rare. All right, next problem. Find a delta G standard value for the following reaction, where 2 golds are oxidized. Haha, how likely is that? Gold, which is very stable, it's used in coins, is going to be reacted with copper? I don't think so. Gold is actually one of the most stable of all elements. But we would like to find the delta G standard for this anyway. And so we can find this by, again, going into the back of the book and finding the free energies of formation of the products and the reactants. Or we can say delta G standard is equal to negative NFE standard of the cell. And so we need to get, in order for this, we need to get N and we need to get E standard of the cell. And so to get N, we have to say how many electrons are being transferred during this. Well, we see that 2 golds are being oxidized into 2 gold 3s. Now when this occurs, balance the charge here. We have a 0 overall charge here, and we originally had a +6 overall charge here. In order to balance the charge, we must add an additional 6 electrons to give now an overall charge of 0, just like on the left. And so we see that there are 6 electrons being released when gold is oxidized, and we see that 3 copper 2s are being reduced to 3 coppers, and in order for that to happen, again, we need to actually absorb 6 electrons. And so 6 electrons are released, 6 electrons are absorbed, N value is 6. And solve now for E cell, it's equal to the E standard cathode minus E standard anode. What is at the cathode? What is being consonant? What is being reduced? Consonant. Copper is being reduced. So we need the standard reduction potential of copper here, and then what is at the anode? What is being oxidized? Gold is being oxidized. Use the standard reduction potential of gold there. Plug in from the standard reduction potential chart, and you find then that the E standard of the cell is negative 1.16 volts. Again, non-spontaneous reaction. And we can plug in here, and we get 672,000 joules per mole. We get this because we had volts canceled out, so that's just joules over moles is left over. And this is also 672 kilojoules per mole. This is a very positive number. This is not very spontaneous at all, which is what you should expect. Gold is not very reactive. Thanks for watching, guys.